So we would like to explain what a linear space is, or rather what a vector space is. And let's agree here that we're going to work over the real numbers. Over the field of real numbers. When we use the word field, we really mean a set over which arithmetic can be done. So it's a set that will allow us to add, subtract, multiply, and divide numbers. And certainly the set of real numbers is such a set. So the prototype for what we're constructing here is Rn. So in Rn, we can do what? So Rn consists of all n tuples of numbers. All of these are real numbers. This symbol means belongs to. And what you can do if you have two such n tuples of numbers is add them up. And we can also scale them by any real number. Using this as a prototype, we're going to call a vector space or a linear space a set equipped with two operations, one of addition and one of scalar multiplication, where 8 properties, 8 axioms will be fulfilled. So the set V equipped with two operations. The first one is addition. In other words, to any two vectors. We associate their sum. So if we have u and v, we associate to them u plus v. And scalar multiplication, it's not by a dot, even though usually the dot is dropped, to any real number lambda and a vector u, we associate lambda u. So you can put a dot or you can just leave it without a dot. Here, let me just specify that when I say vector, I really mean just an element of this set. So, because since we're talking about vector space, its elements are going to be called vectors. But again, the prototype that you should have in mind is Rn. So, this set is going to be called the vector space if it satisfies the following properties. Is called the vector space if it satisfies and here are the properties. So first of all, if you have 3 vectors, you can add first 2 of them and then the third one, or you can add the last 2 and then the first one, and you will get the same thing. So here we say for any, so this symbol here means for any. U, v, w that belong to v. The second property is that there exists a vector 0. I'm denoting it with the 0 because the property that defines or that describes this vector proves that the vector actually is unique. So you can give it a specific symbol. But this vector works in a neutral way when it's being applied to any other vector through addition. Okay, so it doesn't affect any vector when we add to it. And for any vector u, that's the third property, there exists vector v, which is the opposite, meaning u plus v is the same thing as v plus u and it's equal to 0. V will be denoted by negative u. Again, the reason we can give it some notation is because it can be proven to be unique. And we define subtraction. So if, let's say, you have a vector w and you want to subtract u, that's the same thing as adding this vector v. Okay. Or you could say we add the opposite of the vector. And we have one more property here that involves just addition, which is that addition is commutative. So it does, the order in which you add two vectors does not matter. Okay, now we have four more properties that involve multiplication. So first of all, if we want to scale the sum of two vectors, it's the same thing as if we scale the first one and then we scale the second one and we add them up. It works the other way around. So if you want to scale by the sum of two numbers, a given vector u, then you can scale it by the first number, then you can scale it by the second number, and you can add them up. And if you scale a vector by the number 1, then you get the same vector. And finally, if you want to scale a vector by the product of two numbers, you can actually scale it by one of the numbers and then scale it by the other number. So for any u in V, for any lambda comma mu in R. So if a set equipped with two operations satisfies the same properties, then it's called a vector space. And again, our prototype is R to the n. Now, we can also define other more exotic sets. So for example, take as an example the set S of all sequences of real numbers. Then this is a vector space. And if you have a sequence, AN, you can think of it as a vector similar to the ones that we encounter in Rn, but with infinitely many coordinates. So A1, A2, A3, and so on. So when you add two such sequences, you just add them coordinate-wise. And when you scale such a sequence, again, the scaling takes place coordinate-wise. And this is the first example of what is going to be an infinite dimensional space. You will see that later we're going to impose some conditions on these sequences, so we will require them to tend to zero or to be bounded or to have a limit. But this will come later. For the moment being, here's an example of a space that eventually will turn out to be infinite dimensional. And that's all for the definition of a linear space. Thanks for watching.